So 27, these two plus 68 add up to 95. So we just need one of these, so we can solve for it. So x will be 27 over 2, which is 13.5. So what that means is these probabilities are both 0.135. Okay. Now finding the remaining probabilities isn't too bad, I don't think, because we know that so far we've used up 95% of students between B, C, and D. So that means all that's left are 5% of students. Some of them will get an F, some of those will get an A. And again, this distribution is symmetric, so the probability of getting an F is going to equal the probability of getting an A. And we know that those two probabilities have to add up to 5%. So that means each one is going to be half of 5%, or 0.025, 2.5%. Okay. So this doesn't seem like a grading scheme that I would want. I don't want grades divvied up by standard deviations. It puts way too many students in the C range, a pretty small portion in B's and D's, and not very many at all in A's and F's. So splitting by standard deviations, maybe not the best way to go about it. Okay, let's do another example. So what we'll do is we will set this example up, and then we will introduce some calculator functions to actually solve the problem. So 1 year, an exam has an approximately normal distribution. Presumably the scores of that exam follow an approximately normal distribution, with a mean score of 83 and a standard deviation of 5. About what proportion of students would earn a B, where a B is a score between 80 and 90. So you're going to see things like this pretty frequently now. And this is a big clue about what you're working with. So thinking back a little bit, in the problems where we were using the binomial distribution, the more you do, it will become more obvious that you're dealing with a binomial distribution, but you have to do a little bit of work to look for its key characteristics. You're counting successes, you have two outcomes, a success and a failure, and you have independent trials. The way that you will know you're working with a normal distribution is you will see, at least for now, that something is approximately normal. And kind of the interesting thing here is the word approximately. So something that may trip you up as we proceed is that we're going to treat some types of random variables, like exam scores, as following a normal distribution. But in reality, exam scores are not following perfectly a normal distribution. Because what you have to remember is that kind of odd characteristic now. A true normal distribution goes forever. It can have values as big as infinity. It can have values as small as negative infinity. An exam score does not. An exam score is restricted to be between 0 and 100. So when you see the word approximately, what we're saying is the normal distribution is good enough to represent this probability distribution. And what we mean by good enough is if we can go from the mean up and down 3 standard deviations. If those data points seem plausible, if they look okay, then we can just treat this as a normal distribution. We'll be a little artsy. We'll just call it a normal, even though it's not really a normal. And that will allow us to at least get close enough to the right answer. So, as you work through these problems, I suggest that you sketch things out. So we will begin by drawing the normal distribution. And you'll get pretty good at drawing these. So this is the distribution of big X. This is the probability distribution. And in this example, what we're measuring are exam scores. And we have some information about these exam scores. 1, they're approximately normal. 2, the mean is 83. And 3, the standard deviation is 5. So we'll indicate 3 standard deviations up, 3 standard deviations down, and then we can start adding 5 to the mean. So if we go up 1 standard deviation, 83 plus 5 is 88, plus another 5 is 93, plus another 5 is 98. So that's okay. Having an exam score 3 standard deviations above the mean of 98, perfectly fine. Going down 3 standard deviations, so first we have 78, then we have 73, and then we have 68. So from the empirical rule, that's saying that we expect that nearly all exam scores, 99.7% of exam scores, will be between 68 and 98. So there's a very small chance to be above 98 and a very small chance to be below. Okay? So here's what we're working with. And we're going to introduce another distributional notation. So we can abbreviate most of this introductory paragraph by saying that big X, which again just stands for exam scores, is distributed as a normal distribution with a mean of 83 and a standard deviation of 5. Okay. We will see this a lot as we proceed. So again, what this is saying is your random variable, generically called X, so exam scores, are distributed as a normal distribution, and that's just indicated by a capital N. The first number is the mean, the second number is the standard deviation. Sometimes this will be variance, but in this class, the second number in a normal distribution statement is the standard deviation. Okay? So start getting used to this notation, start getting used to these symbols, because as we proceed, we're going to use more and more symbols just to abbreviate things. So there's our normal distribution. Now let's sketch out what we're interested in. We want to know how much of this curve is occupied by students who get a B. And they tell us that's between 80 and 90. So somewhere in here is 80. And somewhere near here is 90. So we want to be between those 2 points. How much of this distribution belongs to this shaded region? And we can do a little bit of guesswork. We see that this point is a little below 1 standard deviation below the mean, or sorry, a little above. And 90 is a little more than 1 standard deviation above the mean. So maybe, if you can imagine, you could shift this over just a little bit, and it would fall sort of around 1 standard deviation above and below the mean. So maybe an initial guess of this is something like 68%. That's not the answer, but our solution should probably be close to this. It's not going to be near 100%, and you can see that visually. It's not going to be near 0%, and you can see that visually. So then the question is, how do you actually find this probability? So here's where I depart from my stat lab. My stat lab is going to say something like, when you look at the homeworks, here's a standard normal table. And you're going to click the link and it's going to bring up a table with a bunch of numbers. You'll see Z's, which stand for Z-scores, and it's dumb. I'm not going to show you how to solve these problems with a standard normal table. And I recognize that this is going to be an issue because if you rely on things like help me solve this, show me an example, those instructions are going to use this standard normal table. I call this method dumb because it's antiquated. There's no reason that anyone should have to look things up in a table. We have calculators. In my job, I do not look up things in tables. I use computers, and computers find these probabilities. The calculator is our little computer. So we can't use the standard normal table. The other solution is to use calculus. We're not going to do that. So the best solution is, again, let's use the calculator. Let's let it find these probabilities for us. So we have a new function. This function here is going to be the workhorse for a little bit. You'll probably end up using this one most often. So the way that you get there is you'll press second vars, and you're looking for normal CDF. So again, this is maybe a point of confusion. When we were in binomial world, we wanted PDF. In normal world, we want CDF. So if we go to that menu, so you press the yellow button, you press the vars button, and then you're in the distributions, you'll see normal PDF and you'll see normal CDF. And if you were doing a binomial problem, you would see binomial PDF and you'd see binomial CDF. In normal world, we don't want the PDF. Forget about PDF. You want CDF. That will be the function we use. And its inputs are a lot like the binomial function. So you will use this function. Its purpose is described in part A. You use this to find a probability from a normal distribution. Anytime you have a question where something is approximately normal and you're asked to find a probability, find a proportion, find a chance, whatever, you will use normal CDF. And this function requires 4 inputs. What's your start value and what's your end value? Meaning, for the section of the normal distribution that you want the probability for, where do you start and where do you end? The last 2 things you specify are, well, what does the distribution look like? What's the mean of this normal distribution and what's the standard deviation? Okay. We'll come back to part C in just a minute. So here's the problem. We want to find the probability that big X is between 80 and 90, when that's represented again by this shaded region. So the way that we find that is we will use the normal CDF function. So the first thing we tell it is that we want to start at a score of 80 and we want to go up to a score of 90. And again, we're separating these things by commas. The mean of this distribution was 83 and the standard deviation was 5. So let's enter that into the calculator and see what we get. So we start at 80. Again, the comma button is above 7, comma. We're ending at 90. The mean is 83, and the standard deviation is 5. So you press enter, and there's your probability. 0.064499. We'll just call that 0.645. And that's the answer. So if you wanted to interpret this, this means something like about 64.5% of students will earn a B on this exam. The question was, what proportion of students will earn a B? We've just found that it's about 64.5. And the good news, that matched our first guess. So we will commonly use the empirical rule to kind of guesstimate what the solution should be. We thought it would be near 68%, and it's 64.5%. So this seems to match the intuition from the empirical rule, so I'm confident that this is the solution. Okay. There is another calculator function that we will make use of, and that's described in number 2, and it's called the inverse normal. We'll see this in another example soon, and you know that you will need to use this function when you're being asked to find a value of your random variable. So what that means is you'll be given probabilities, and you'll be asked to find, say, an exam score. So maybe a question would say something like, about 64.5% of students will have an exam score between which two values? So it's an inverted problem. It's the backwards version of what we just found. So if you're being asked to find a score or a height or a weight or something like that, then you use inverse normal.